Hello and salam sejahtera. I'm Jana Ibrahim and this video is about Basic FET Amplifier. In previous discussion, you already know that the FET operates in saturation region. We know how to solve DC analysis of the FET. For a common source configuration, we start at the gate source input loop, and we also know there is no gate current or IG equal to 0. To start the analysis, we assume that the FET is in saturation and use the current formula in saturation mode to find ID. Next, we find the VDS at the drain source loop by using the KVL equation. And then compare the VDS value with the VDS saturation to confirm our assumption that the circuit is indeed in saturation region. If the assumption is wrong, we need to repeat the process to find ID using the non-saturation ID formula. Once we know the ID value of the circuit, we can now start our AC analysis. In this video, we will discuss how to find AC parameters and solve FET amplifier requirements in AC analysis. This figure shows the NMOS common source circuit with time-varying voltage in series with the DC source. Let's assume the time-varying input signal is sinusoidal. The graph next to it shows the FET characteristic, DC load line and Q point. The DC load line and Q point are functions of VGS, VDD, and RD. To get linear output of the common source amplifier, the FET must be biased in saturation region. A linear operation of an amplifier is when a symmetrical sinusoidal signal is applied to the input of the amplifier, and we require a symmetrical signal to be generated at the output. We can use the load line to determine the maximum output symmetrical swing. If the output exceeds the limit either on the upper portion or the lower portion of the signal, a part of the signal will be clipped and the signal will be distorted. In the case of FET, the output signal must not be in cutoff or ID equal to 0 and must stay in saturation region, or VDS must be greater than VDS saturation. Now let's discuss about the AC parameters of FET. To solve AC analysis, we need to take out the DC source. The ID versus VGS plot in saturation region is given in this figure. The transconductance Gm is the slope of the curve. If the time-varying signal VGS is small enough in response to the ID, the Gm will be constant. Note that with the Q point in the saturation region, the FET operates as a current source that is linearly controlled by VGS. The Gm is equal to ID over VGS, and this is also equal to 2 times square root Kn multiplied with IDQ. We can see that the Gm is directly proportional to the Kn, or the conduction parameter, which in turn is a function of width to length ratio, or W over L. Hence, an increment in width of the transistor will increase the Gm, or gain of the transistor. In our initial assumption, we assume that the signal frequency is small enough so that any capacitance at the gate terminal can be neglected, which means the input to the gate looks like an open circuit or infinite resistance. The simplified equivalent circuit is shown here. The equivalent circuit can be expanded to take into account the finite output resistance RO, where this is the result of non-zero sloped in ID versus VDS curve. In a nutshell, the small signal drain current ID is related to the small signal gate to source voltage VGS by the transconductance GM. The transistor output resistance RO is equal to VA over IDQ, and VA here is equal to 1 over lambda. Lambda is the channel length modulation parameter and is positive in value. Take note that both GM and RO are functions of Q point parameter IDQ. Therefore, it is really important to do DC analysis and find the correct IDQ value. Once we transform the FET into its AC equivalent, we then can draw the complete circuit, which include VI, the AC source, and RD. The common source configuration is the basic FET amplifier circuit. The output is measured at the drain, while the input is coupled to the gate through the coupling capacitor. In this course, we will discuss 3 types of common source configuration: source grounded, with source resistor Rs, and with bypass capacitor Cs. Here we have the basic common source circuit with voltage divider biasing. Note that the source is at ground potential. The DC biasing is established by R1 and R2. At first, the FET must be changed into its AC equivalent, with between the gate and the source terminal is changed to open circuit. And between the drain and the source, we locate the dependent current control source and the transistor output resistance in parallel. To complete the circuit at gate, we draw the R1 parallel to R2 and followed by RS with AC source in series. At the drain, draw the RD and V out. Let's try an example. Here we are required to determine the voltage gain AV and current gain AI of the common source configuration. The transistor parameters are VTN equal to 0.8 volt, Kn equal to 0.2 milliampere over V volt squared, and lambda equal to 0. By solving the voltage divider biasing, we got RTH equal to 168 kilo ohm and VTH equal to 1.905 volt. Next, we need to do DC analysis to find the DC parameter IDQ. We got IDQ equal to 0.244 milliampere, and from there the GM is equal to 0.442 millivolt per ampere. Since lambda is infinity, the RO is equal to open circuit. Now we start to find the Vout equation by looking at the drain output loop. The equivalent resistance at the output side, Rout, is equal to RD. Then we write the Vout equation where Vout is equal to minus GMVGS times Rout. Next, we get VGS in terms of Vin. By using voltage divider, VGS will be equal to 198.1 over 198.1 plus 0.5, and this is equal to 0.9975 Vin. Hence, Vin is equal to 1.0025 VGS. Finally, we go back to the Vout equation and calculate the voltage gain AV. AV is equal to Vout over Vin, and this is equal to minus 4.42 VGS over 1.0025 VGS. And finally, we get AV is equal to minus 4.41. For the current gain AI, we need to find the Iout equation. Iout is equal to Vout over RD, and it is equal to Vout over 10. Then we need to get the Iin equation at the input side. Iin is equal to Vin over Rs plus Rth, and this is equal to Vin over 198.6. Finally, the current gain is equal to Iout over Iin, and this is equal to minus 4.41 times 19.86, and this is equal to minus 87.58. That wraps our discussion on FET basic amplifier circuit using common source configuration. Thank you for watching, and see you again in my next video.